Hello, my name is Mihm. I am a third-year graduate student in the Shepherd Group at the University of Iowa, and today I would like to tell you about the finite size effects convergence rate analysis I conducted on coupled cluster doubles in the uniform electron gas. Recently, we observed a power law behavior of n to the negative one-third for the convergence of the finite size effects of coupled cluster correlation energy to the thermodynamic limit. This power law was surprising as it was different than the typically accepted n to the negative 1 convergence rate for total energy. For our calculations, we use a simple model of a metal called the uniform electron gas, or the UEG, which has a uniform positive background with negatively charged particles that are allowed to freely interact. For the UEG, we work in momentum space where each orbital is distinguished by the quantum number q. This allows us to run the wave function-based calculations coupled cluster doubles. We use coupled cluster theory for this study because it is exact in the high density limit, or the low RS, of the electron gas and will extrapolate to exact analytical limits. Thus, it allows us to investigate the convergence rate of the correlation energy to the thermodynamic limit. As we work with solids, one of our largest sources of errors is the finite size effects, which comes from modeling something really big, like bulk, from something really small, such as a 2x2x2 supercell. One of the common methods of reducing this error is twist averaging, which requires averaging over multiple coupled cluster calculations at different twist angles. However, this method tends to be very expensive. We have developed a method of twist averaging called connectivity twist averaging that finds a special twist angle that models the average system that we can use to run a single coupled cluster double calculation, and that produces comparable results to conventional twist averaging across a range of system sizes, as seen in the bar graph. The advantage of this method is that, due to the cost reduction, I can run calculations at system sizes 3 times larger than what twist averaging allows. We use this new method to run calculations for system sizes from 14 electrons up to about 1800 electrons for different densities, labeled as RS in the graph. This allows us to get a clear picture of the convergence of the coupled cluster correlation energy to the thermodynamic limit. This convergence rate is measured by the convergence of the finite size effects of the system, shown here on a log-log plot. The power law for the convergence rate can be measured as the slope of the line fit to the data, shown as a dashed line. When we evaluated the power law for this convergence, we found both densities converged at a rate of about n to the negative one-third. Our most recent analysis shows this is due to the fact that the finite size effects are larger for small electron gases than expected. Eventually, we would expect this convergence to be n to the negative one-third convergence. In conclusion, our analysis of the coupled cluster correlation finite size effects convergence rate shows an n to the negative one-third convergence to the thermodynamic limit. We believe that this will eventually cross back over into the n to the negative 1 convergence. These results are surprising and indicate that the power law is significant enough to be worth further investigation. I'd now like to say thanks to the Shepherd Group and to my advisor, Dr. James Shepherd, for allowing me to work on this project. I'd like to thank my collaborator, Bindi Yang, for helping me throughout this project, and I'd like to thank the University of Iowa and the Iowa Informatics Initiative for funding this project, and I'd like to thank you for listening.